Okay, this video is a tutorial about some of the concepts that you'll see in Objective 204.2. Let's look at an overview of 204.2 worksheet questions. Some of them can be found in electrical systems, so do your reading. Some of the questions can be found straight from the code about conductors. And some of the questions are nowhere to be found in the curriculum yet. And so that's super sad. And they're assuming that you have some background in theory about neutral current and how that looks for some of these questions. So hopefully this tutorial will help fill some of the gaps where there isn't curriculum material. Let's look at the title and the concepts of 204.2, and I think this will help you understand why there's such a mix of different kinds of questions in this worksheet. It says, possess a fundamental understanding of ampacity, insulation ratings, and ambient temperature of circuit conductors. Okay, so that's a lot. Let's see if we can break down what they translate that to mean as far as the worksheet questions. You will see questions that deal primarily with the 75-degree column versus the 90-degree column in 31015b16. Now, what I mean by 75 versus 90 is the question is going to see if you know when to use which column. And before I go on, let me just distinguish those two really quickly. In the 75-degree column, you see the different insulation temperature ratings for the insulation, and then you see in the 90-degree column, the 75-degree column is where we are going to be limited to whenever we are sizing conductors in a circuit, meaning if they indicate that there is a circuit going on with a load and an overcurrent protection device, we will be in the 75-degree column. Except when we are making an ampacity adjustment or correction, meaning we're going to adjust for more than 3 current carrying conductors in a raceway or correct for ambient temperature that's different than 30 degrees Celsius. I might have gotten the terms wrong there, adjustment and correction, but when you see a worksheet question that asks you what the ampacity of the conductor is when there's 6 current carrying conductors in a raceway that is going to go through a 135-degree temperature area, then you know to size your conductors out of the 90-degree column. And there's code to back that up, but let me just throw that out there really quickly. So back to the title of our objective. They're also going to ask you questions about continuous versus non-continuous loads. And we'll get into that here in just a second. Ohm's law plus the continuous load rule. So now they're going to layer your understanding a little bit with more than one concept. And then single phase loads sharing a neutral. We're going to get into that. They throw even some of your understanding about the small conductor rule in on some of this, where you have to go through the process and size the conductor and then step back and look at it and see if it violates the small conductor rule in 240.4. And then also they have some questions in here that make you do some corrections and adjustments. So let's get right into these different kinds of questions. The 75 versus the 90-degree columns in 31015b16. These are a couple of codes that I would encourage you strongly to highlight. 110.14c, all of it, including its subsections, and 310.15a3 teach us about how the temperature rating of a conductor has to be limited and coordinated to match the temperature rating of any termination. And since in the world 95% of the terminations are rated for 75 degrees, the curriculum has chosen to make you assume that all temperature rating or terminations are at 75 degrees. So our world is going to be the 75-degree column when we're talking about circuits, except of course those adjustments and corrections that I told you about a second ago. 110.14c also gives us the go-ahead to use that 90-degree column when we're making the adjustments. A few of the worksheet questions are not necessarily making you do the math to use the adjustment and correction factors, like those percentages and little decimals, but rather it's going to test your understanding of the concept that when a 90-degree conductor is tied to a 75-degree termination, then the conductor ampacity actually has to be chosen from the 75-degree column. So just kind of what we've been talking about already. Let's see what it looks like in a question. Where a 2-aught gauge THHN, that's a 90-degree column, THWN copper conductor is inside a panel board and is connected to a breaker, how much current can it carry? Let's break this down a little bit. Where they say inside a panel board, they're trying to make you visualize that we're not in a raceway with more than 3 conductors. So we are going to be in 310.15b16. Connected to a breaker. This is where the question is trying to help you know to be in the 75-degree column, even though the THHN, THWN is a dual-rated conductor. Can carry. I'm not in love with those words in this question. It would be more accurate to say is permitted by the code to carry, because a THHN, THWN copper conductor can carry what the 90-degree column says it can. But in this scenario where we are tying it to a breaker, the code limits us to the 75-degree column. Okay, and there's our answer. 75-degree column, 2-aught gauge copper, 175 amps. Now on to continuous versus non-continuous loads. 210.19a. Definitely highlight this. Make it a flashcard if you haven't already. This is the rule about continuous loads and non-continuous loads for conductor sizing. In 210.20a, we find the rule about overcurrent protection for continuous loads. Same rule. You know this by heart. Continuous loads are sized at 125% and non-continuous loads are sized at 100%. And then throw one more code into your reservoir. This is another one it would be good to highlight and make a flashcard for. 424.3b. This tells us that fixed space heating equipment shall be considered continuous. And I mention this because the code often will give you a question, or your journeyman test will give you a question and they'll mention a boiler or a fixed space heater or an electric heater. They'll just mention an electric heater and ask you to size the conductors for it, and they're not going to remind you that fixed space heating equipment is considered continuous. You have to just remember that. That has to become second nature. So let's look at a question. 2 loads are to be connected to a branch circuit. Load number 1 will draw 35 amps and operate continuously, and load number 2 is non-continuous and will draw 42 amps. What size THHN, THWN copper conductors are permitted for the branch circuit? And we can see it's branch circuit. We're going to assume we've got a breaker. Let's analyze it a little bit. Continuous load is going to be 125%. Our non-continuous load at 100%. And then we're going to be in the 75-degree column. Now let's put it all together. 35 at 125%, 42 amps at 100%, equals 85.75, which is basically 86 amps that we need a good wire size for in the 75-degree column. 3 gauge will do it. Okie dokie. Now for the questions that are going to combine some of your skills. Ohm's law plus continuous loads. We're just going to jump right into an example. A 12.5 kW 240 volt electric furnace is fed from a 2-pole breaker in a panel. What minimum size conductors are required to serve the furnace? All right, it didn't specify the current draw, the load of this this furnace, so we're going to have to do some math because you have to have the load in current in order to size conductors. It is fixed electric equipment, so space heating equipment, so we know to consider it continuous. Sorry, I meant to put heating in there. And then the panel indicates that we've got a breaker, so we know that we need to be in the 75-degree column. So you can see how subtle it is sometimes with these questions. They really make you extrapolate information that you're going to have to tie the codes to. So here's the math. 12,500 watts divided by 240 volts. So we have P over E equals I, and that's 52.08, which is basically 52 amps. Continuous load is 65. In the 75-degree column will be 6 gauge. Okay, and now on to single-phase loads sharing a neutral. This is not terribly detailed in the curriculum. So this is something they just assume we've kind of learned. Let's go over it though. In electrical systems, there is a mention of the fact that the grounded conductor carries return circuit current. So we know that the neutral carries current, but how much current does it carry? And is it affected by, is there an effect when a neutral is shared by loads on 2 different phases? There is a complex 3-phase neutral current calculation in UGLES. You do not need it for these problems. These are single-phase loads, and they're kind of simple once you know what to do. You really need to have a solid understanding of voltage systems, 3-phase and single-phase, and how these look in a panel. So let's just go over that really quickly. In a single-phase 120-240 volt panel, every other pair of circuits changes phase. So circuits 1 and 2 are in A phase, 3 and 4 are on B phase, 5 and 6 are back on A phase, etc. In a 3-phase panel, a 120-208Y, a 240-120 3-phase delta, a 277-480 Y configure, the pairs of circuits alternate between A, B, and C phases. So circuits 1 and 2 are on A phase, circuits 3 and 4 are on B phase, and circuits 5 and 6 are on C phase, and then it just repeats. So let's look at an example. We have here a panel schedule. You may have seen this before. And it's coming from a 120-240 volt single phase 3-wire panel, although it could have been coming out of a 3-phase panel. Either way, it's not going to make a difference if it came out of a 3-phase or a single phase, because the loads in our question are just single phase loads. So it's talking about if circuits 2 and circuits 6 share a neutral, there should be how many amps flowing in the neutral. Let's skip over here. The neutral current for single phase loads is the unbalance between the loads. So it is the difference, where we're going to subtract, between the loads when they're on different phases. So let's see what that looks like. We have circuit 2, which was a 1.5 kVA load, and circuit 6, which is a 1.4 kVA load. So we're going to subtract one of those from the other, and that's going to be what the neutral sees. It's kind of funky, but it works. Let's look at the math. 1500 divided by 120, so we did a P over V equals, P over E equals I both times, and then did the subtraction. So the neutral current on that shared neutral is 0.8. Now another problem, same panel, different loads. This time circuits 5 and 6 are sharing a neutral. How many amps should be flowing on it? Single phase loads. Let's look at loads. We've got, let's just talk about neutral current first. When loads are on the same phase, which 5 and 6 are on the same phase in either a single phase panel or a 3-phase panel. It doesn't matter. 5 and 6 are on the same phase. The neutral currents add. So there's our 1.4 kVA load, 1.4 kVA load. So now we need to do some Ohm's law and find some current and then add it together. 1400 divided by 120 plus 1400 divided by 120 equals 23.33 amps. So on either one of the hots, you're going to see like 12 amps, but on the neutral, it adds to be 23.33 amps. Ouch. Okay, and then finally, there are some questions that make you do calculations to adjust or correct the conductor ampacity, and I've done a whole other video on that. So please refer to that video to help you with those problems.